Thank you, Jennifer. All right, so you already sat and looked at the overview slide, so I'll show you a better overview slide here. We're going to talk about three different sites, and this is, where they overlap. They're all TCE is the major contaminant, trichloroethylene, and it's DNAPL at all of the sites. And contaminated soil, groundwater, soil vapor. So a subslab depressurization system is going to be part of the remedy for any buildings that go up at the sites. So this morning, David talked to you about the EPA FS system and those threshold criteria, those primary objectives: protect human and environmental health and comply with whatever regulations are in place. At the Superfund site, it would be EPA. At state sites, it's going to come under state regulations. And two of our sites are in Massachusetts. Massachusetts does have a prescriptive way of going through the feasibility. And however, you still have those threshold criteria of protecting human health and the environment and complying with the regulations. And the regulations you're complying with under the MCP plan are these spokes on the outside of that wheel. Each one of those is a specific regulation that you have to consider when you're looking at the feasibility requirements. So this first site, oh, excuse me, not on this site yet. You've got the MCP approach. The prescription as you go through these 5 different phases. The one that controls the feasibility study is the phase 3. And each of those numbers and the website, anything you want to know will be there. In terms of the details, those are the specific numbers for the regulations for each point. So the health center, it has some overlap with all of these sites, and two of the sites we're going to talk about fall under the MCP site. They're MCP sites. They're in Massachusetts, of course. And this was a brownfield site owned by the state of Massachusetts, and there was a health organization in the area that needed land to build a new health clinic to service the community. And so they came with an agreement with the state of Massachusetts, a long-term, low-cost lease with the stipulation that the health organization would clean up the site. So, the construction had to happen at the same time as the remediation. So that posed some challenges. And the reason we did the full FS is there was no imminent hazard. There was no building on there right now, and as the building was going up, we could incorporate protective measures. And we knew that we were going to go to full-scale remediation, so we need a full FS. So there's basically all the site media were contaminated. The receptors were really future receptors, the health clinic, which wasn't built yet at the time of the phase 3, and also the neighboring properties, which are under development. They were unoccupied at the time. And this is an overhead view of the site after the health center was built, and just the earlier slide where you saw that brick building, that's actually at the north, at the top of the slide, and the health center is in the south part of the site, bottom of the slide, and that's just, it can serve the community better. That's just it's on a better road. You can see that the TCE source area, 200 milligrams per liter, quite a bit of contamination there. So we didn't look at the world of remedies, but these are some of the common remedies that were considered and evaluated, and a few of them were just discarded. Obviously, you've got DNAPL. You probably no further action is probably not a solution. M&A for the plume, yes, but not necessarily for the source area. And we also discarded the permeable reactive barrier initially because of the cost. However, we did end up employing it for the second phase of the remedy, and I'll talk to you about that later. The site soil is very silty, so pump and treat and air spray RHSV, that was not going to be a particularly useful remedy. Same thing with, ISCO in terms of cost. So we ended up narrowing it down to 2 source area options and 2 plume options. And in both cases, the building had to be protected with an FSDS, and there had to also be institutional controls on AUL. So a comparison, we chose high vacuum extraction for the source area and enhanced reductant chlorination for the plume area, based on cost, timeliness, and efficacy. So during the you're looking at the containment area, those groundwater contours are showing the time of the HVAC system was in operation, and the reason that we chose HVE and rather than just an ordinary pump and treat is, I love this picture. Is one of my favorites. Dr. John Wilson, who many of you know, took this about almost 30 years ago, and it's a cross section, photomicrograph cross section of a soil pore in sandy soil, and you can see that blob of DNAPL, which could be TCE, could be PCE. And the goal of the HVAC system is actually apply enough vacuum that you can actually try and pull some of that NAPL out of the soil pores. And it was effective to a certain extent. I mean, obviously you can imagine it's not going to get them all out, but it definitely helped, and we were able to remove some source material. So that operated for 2 years, and what you're looking at here is the plume a year after the HVAC system was shut down. You can see there's some rebound in the source area. And we will be applying additional remedy in the source area later. What we did is at that 1 year point was to treat the plume by installing plume stop, injecting plume stop, which is one of your sponsors is Regenesis, and that's a Regenesis product. What it is it's 1 to 2 micron activated carbon, and it's becomes a colloidal solution that it's the viscosity of water, very easy to inject. The particles all have this polymeric coating on them that biodegrades over time, and so for a few weeks the product will move with the groundwater, and then as the coating degrades, it drops out and sticks to the soil, sticks to itself, and basically becomes this in situ reactive barrier. And plus it's, not only is the TC absorbing to it, but bacteria growing on the surfaces. And you just have this wonderful improvement in contact. And Paul's gonna talk a lot about contact at the end of the day, because it's contact, nothing can happen. If you've got, especially once you get down below 100 ppd, it's just so hard for anything to work. You've got these TC molecules bouncing around in a soil pore. They have to hit a wall in order to hit the bacteria that are going to degrade them. Bacteria aren't working swimming around in the soil pore. They're working growing in biofilms on the walls of the soil pore, on the soil particle surfaces. So this works. And the reason there's 2 of those instead of just like one nice one is all of that lighter colored pavement that you're looking at, and that's the parking area to the north, is pervious pavement. So we didn't want to disturb that at all. So we put these 2 barriers in. And you can see 1 year after the injection that's it's definitely working nicely. The northern one is working a little bit better. We still have that rebound in the source area. So what we ended up doing in the source areas, we used the former extraction wells to inject some additional organic carbon to stimulate reductive dechlorination in the source area, and that's working very nicely too. And we have to, in order to be able to close the site out, have to continue to maintain the indoor air concentrations below the vapor intrusion threshold. There is a liquid boot underneath the building, as well as a crawl space for active ventilation. So this is the health center with a summary of everything that was done. And their remediation activities happened at the same time as the building. The health center was in operation from 2015 on. And if you look at the left-hand picture, you can see those gray boxes behind the building. That's where the HVAC system was. And to the left of the sidewalk in that landscaped area, that's where the extraction wells are. Well, now they're injection wells, but they're still there. All right, now I'm going to turn you over to Mary Ann. She's going to talk to you about a site in California with very different, similar contaminant, but a lot of differences.
Thanks, Karen. So the California site that I'm going to talk about also had TCE, DNAPL in soil, groundwater, soil vapor. We use a lot of different technologies out there, and the California regulatory regime is a bit different. So, especially coming from Massachusetts, so go through that. It was a former industrial plant that manufactured capacitors and filters from the 1950s on. They left the site in the early 70s. It was some light industrial through the early 80s and commercial thereafter. There's the main COCs, TCEs associated with historic degreasing, but PCBs were used for a limited period of time. The geology out there is a little different than a lot of my sites back east. We have like 2 aquifers. First one's down at 20 feet, sandy. There's an aquitard between them, but there is some communication. The vadose zone is really, really tight, silts and sands and a lot of clay. And the aquifers themselves are very permeable. So picture like a medium aquarium sand to get a feeling for how fast water can run through this site. The lead agency out there is the Department of Toxic Substances Control, DTSC. And in California, there's actually 2 agencies, and they operate on a county-wide basis. They each have their own kind of shtick where DTSC does a lot of the guidance documents, and the regional board is in charge of protecting the aquifer. But in general, if you have an environmental site, it could be under either jurisdiction, or if it's a very basic and simple site, like a tank pull or a small excavation, it can be done under the lead of the fire department. And so why do we go full scale here? Well, the full scale process of FS is pretty much identical to the EPA process. In fact, the FS for our site, which was submitted in 2005, references that 1988 EPA guidance as a governing document. And according to DTSC, they have this comment on their website about the process applying to larger, technically complicated sites where you anticipate a cleanup action. And so unlike are most of you guys from Massachusetts? Do you guys work in Massachusetts? Hands. Oh, awesome. So picture not that, like at all. So the first boring was put in 1986, and through the late 90s, early 2000, they went through the RI process in soil, then in groundwater, risk assessment went in 2004, then the RAP. All of these require comments back and forth, 2 to 5 iterations per report, all culminating in the consent decree and statement of work, and followed by a remedial design document. Again, all of these things need to be approved. So yeah, not Massachusetts. So for this site, we went through all the same remedial technologies, a lot of the ones that you saw on Karen's slides. And like Massachusetts, EPA, we carry no further action initially as a basis of comparison, but this site's really small. It's only just over an acre in size. So things like slurry walls, pump and treat, things that required permanent infrastructure wasn't going to work for the site. And because there's a lot of DNAPL in the subsurface, things like bio and phytoremediation and surfactants weren't really going to be applicable for this site. What we ended up doing was we looked at things that would not require a lot of permanent infrastructure on our site. So we compared in situ thermal treatment, ISTT, with ISCO, and we compared these based on, how quick it would be, how effective, and the cost. And you wouldn't initially think of ISTT as a cost-effective option, but it is when you factor in the value of these properties. So it's in a pretty ritzy area, and this whole area was transferred from being like industrial to sort of fancy residential communities. So you can file this under time is money. For California, one thing that's a little interesting for this site that's different from a lot of my East Coast sites is the groundwater monitoring and the soil vapor survey were actually part of the remedy, not just things you did to prove that your remedy was effective, but actually put into the prescription for the remedy, which is a little different from what I've worked on here. And so here we have our list of remedial strategies, which is kind of a lot of remedial strategies for a 1 acre parcel. And they each had their own remedial goal. The PCB excavation was a numerical goal, so basically back calculated allowable concentration to get us there. The monitoring had a lofty goal of protecting the deeper aquifer and ultimately reaching MCLs, because in this area, all groundwater is a potential drinking water source, even if it's not, even if it's brackish. Yeah, I guess that's optimistic of them. The thermal treatment, the remedial goal was actually level of effort based. It was written into the statement of work that it was going to reach the limits of the technology, i.e. asymptotic conditions. And so that was very prescriptive, and in all of our following documents, all the design reports, the REP, everything quotes that was going to be the final answer. SVE was incorporated into the design to protect nearby abutters, and ISTO was included as a contingency plan. And what I mean by that is, if the concentrations in the groundwater outside of the thermal treatment area were to increase, ISTO is going to be performed to deal with that. And like I said before, soil vapor sampling is actually in the remedy. What that was going to do is that provided the basis for any future institutional or engineering controls. So before we dive into the strategies, here we have our site to get oriented. So here's the parcel, the subject property. So although the plume, goes off property a little bit, we were limited to work in this area. The groundwater flow is south-southwest, and here we have the DNAPL source zone. And that source zone was defined again in the documents. So not my opinion, but it is the source zone. So we'll start with excavation, one of the simpler strategies we used on site. We had a few excavations to remove the PCBs from the vadose zone. We had a larger area between the buildings, and then we had these spot excavations. We pre-characterized to allow for live loading because the site was small and it was going to be pretty inaccessible during the excavation activities. There was one excavation that was close to the corner of a building that actually went down to 20 feet. So that provided some fun engineering design issues, given the, like I said, proximity to the building and California regulations involving, lots and lots of permits and worrying about earthquakes. So like I said, groundwater was in part of the remedy. So here we have our TCE plume in the deeper of those 2 sandy aquifers. As you can see, a fair portion of subject property has concentrations exceeding 50 ppm, with the highest concentrations in the hundreds of ppm. And now getting to the good stuff, ISTT. So here we have a view of our site, and this was going to be our ISTT area. Again, you'll notice it's the same as that DNAPL source area. And so I'm not sure how many people have actually employed this technology, so I'll kind of go through the nuts and bolts of it. So in the traditional sense, you want to heat up the soil, groundwater, soil vapor, all that nonsense, get it to boiling, boil off the contaminants and treat it. The ISTT can be conductive or resistive. So on this site, we did resistive heating. Just comes down to Ohm's law, V equals IR. You take some current, put it in the ground, use the resistivity of the soil. That provides your power density. Yeah, so that's that. This is what an electrode looks like. Pretty similar to putting in your regular old-fashioned wells. Some slight modifications. The backfill is conductive backfill. On this design, it was 1 part shot and 1 part graphite. The shallow electrode served 2 purposes. It was made of steel, so hooked to a cable, actually delivering current to the vadose zone, but also slotted like an SVU well to remove steam. Deeper electrode was just basically a copper plate. And we had a drip tube that provided water to the backfill to keep it moist, because unlike conductive heating, this doesn't work if you desiccate the soils. It needs to be wet to provide that resistance. So here we have a view of our whole site, the electrodes. This was, the PCU, power control unit. This system was sized for 500 SEFM and 500 kilowatts. So once it was pulled out, it goes through the cooling tower and condenses out the liquids. And from there, it's pretty much like an SV system. Lower carbon, or carbon in this case, but thermox, catox, and other technologies. So yeah, how do we do? Really well, actually. I love this graph because it looks like what vendors give you while you're bidding the project. Like, it's like low, 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 target temperature, low, 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 low. And so I love this graph. The end part meets the definition of asymptotic that we included in all the design documents, which was mathematical and very prescriptive. It had to be this slope, not that slope. And yeah, so it was great. We're very, very pleased. You saw the circle, it was 30 feet down to 50 feet. We pulled out over 1,000 pounds, I think it was 1,062 in 5.5 weeks from a 30-foot circle. So we're very, very pleased. But remember that contingency plan we talked about? We were gonna end up needing it. Sure, you guys all remember college chemistry really, really well. And the fact that as you heat up water, VOCs become more soluble and the mass flux increases. So you can imagine where you've started heating up your area, but you're not quite boiling, and the water's passing through, and it hits some dirty dirt outside of the ERH area, and basically solubilizes previously steady state impacts. And so you have a temporary increase in your concentration. And so that happened here. You can see our ERH area in red and our downgradient well in green. And it's low and slow. And we start heating and woo, then contingency plan goes back down again. And so what did the contingency plan look like? Basic ISCO, we had 7 points, direct push. We ended up putting in 8,000 gallons of 5% solution. You can see the ISCO points are basically just down gradient of the ERH area. And it worked really well because you remember how I talked about that medium aquarium sand? Chemox is so great in sand, I have to say. We injected under pressure, flooded the pores, and it just worked really well. And so where are we now? TCE contours, pre-remediation. TCE contours a couple of years ago, we did our confirmatory sampling. So as you can see, concentrations have gone down a lot, but there's still downgradient impacts, as you'd expect for only remediating a 30-foot circle. You know, can't expect miracles. And the technology was effective, it was fast, it was really great in a lot of ways, but personally, and especially coming from Massachusetts, I felt like the process out there, the rod, having all of that laid out for you was like having handcuffs on. You can't change after the fact. You can't reopen the rod. If you try to, it involves a lot of attorneys. So any innovation, anything you think of after the fact that was like, oh, we could do this, that would be cool, that would be great to supplement the remedy, kind of can't do. And that is a bummer because in 1986, the first well went in. The remedial design wasn't approved until 2008. The technology's changed. All this stuff that we didn't have, we have now. So I say let's go back to Massachusetts where life makes sense for the last case study. So our final case study, like the other ones, TCE, DNAPL, groundwater. Couple notable differences for this site is one, it's in fractured bedrock. So now we have DNAPL 100 so feet down. The second thing is proximate to a drinking water source. So that means that the on-property water is not GW1, but the off-property portion of the plume is. So you guys know that for most contaminants, that's equal to the MCLs. That's kind of driving the remediation out there. It is, like a lot of my sites, it's an old historic factory that manufactured equipment back in the 50s. The site was vacant through late 90s, early 2000s. And we have blasted rock, kind of granular fill, glacial till underneath that, bedrock underneath that. The till is, you know, really, really tough. It's really dense, sand and silt. And the bedrock is more like moderately fractured, moderately weathered, granitic, nice, and it's got some steep angle fractures. Like I said, this is proximate to a drinking water source. We've got the fractures kind of governing the secondary porosity and the hydraulic conductivity of the bedrock. So that, you know, decreases with depth as the frequency of the fractures decreases. Main COC is TCE. We had concentrations in the hundreds of ppm, again, greater than 10% of the aqueous solubility. And we ended up installing a groundwater containment system as an immediate response action because they saw free floater, nope, not floater, free NAPL, I guess, in 2 monitoring wells on site. So literally inches of DNAPL. And so this is proximate to a drinking water. So the system was installed with great urgency to protect that drinking water source. And so it was done as an IRA, and the MCP process was sort of happening parallel path while we did the pumping tests and all the other things you do to design a hydraulic containment system. And so About a year and a half after the system was designed, we were up to phase 3. We got through phase 2, nature extent on the risk assessment, and we're looking at the phase 3. So like I said, we carried no further action as a baseline for comparison. But where this was a little different is we already had a system, right? You still need to go through this process though, because we have to make sure, is there anything better? Is there anything we're not thinking of? We have to review if there's any additional technologies that we should look at now that the pressure's off, now that the plume is contained and not going to this drinking water source. And so due to the nature of the hydrogeology as well as the contaminants, certain things dropped out right away. We weren't going to be doing any sort of like barriers because it would require excavating hundreds of feet of bedrock. Similarly, injecting things like air, chemicals, surfactants, all of that stuff made us a little leery because of the potential for uncontrolled pathways due to interconnected and the whole nature of fractures. And so in the end, we ended up looking at the pump and treat system, and with the risk assessment in mind, we knew that there was no risk to facility workers. There was no substantial hazard. So do we actually even need a system? And if we do need a system, does it need to pump in the source area, or does it just need to provide containment? And is the system we have the best system, or should we be looking elsewhere? So this phase 3 was a little different than our normal one because it was focused on, how can we make this better? Are there any other technologies? But is there a marginal benefit to expanding the IRA system? So in the end, it turns out no. More wells were going to be really, really expensive, but this is why it pays to do really long and really comprehensive pumping tests, because even when we modeled adding additional wells, we would get marginal benefit for a lot of cost. The site was going to be redeveloped, so an SSDS and AUL was going to be pulled into that process. And in the end, now we have a pump and treat system. And since inception, it has pumped tens of thousands of pounds of VOCs over the years. And pump and treat is effective. We all know it's effective, but we still have concentrations that are greater than 1% of solubility and other evidence of DNAPL impacts remaining. And so this is right around the time where I made my first trip to the site, which was while I was being interviewed at GZA. So I'd gone through the first round of interviews and I went through the second round of interviews. And towards the end of the second day, they said, hey, do you want to see one of our treatment systems? And I was like, oh yeah, I really want to see his treatment system. So we drove out to the treatment system and I walked into the building and I just in awe. If you were here yesterday, you heard this story, but still near and dear to my heart. Looking at all the pumps and the gauges, and I was like, this is the height of technology. Like, this is the fanciest thing I've ever seen. And this is a pump and treat. This is a 90s era pump and treat system. So yeah, I remember thinking it was amazing. And just so you get a feel for where this technology has gone and where it's been and where it's going, this gentleman right here, who is looking at the off-gas controls of a similar system, is now the CEO of GZA. And so it's old school. It's no longer the gold standard for DNAPL sites in fractured bedrock. It's still tried and true if you need to have capture, especially for protecting a drinking water source. But now, all these years later, there's other stuff we can do. And so to that end, Karen's gonna shed some light on that.
Thank you, Marianne. So is there something else we can do? Is there something, or is there something supplemental we can do? Is there some way to get rid of some of this DNAPL so that maybe the pump and treat system could be shut down eventually, possibly, or minimize, maybe less wells? So in order to do that, in order to evaluate remedies, we really had to do, basically almost go through a whole new remedial investigation. And we used physical, chemical, and biological tools to do that. And some tools that were old and had been around, but maybe we were applying them a little differently, and some tools that we just didn't even have 20 years ago. So we looked shallow and deep source area, shallow and deep down gradient. And for the geophysical investigation, some of the things, these are some of the things that we did. And here's a picture of a heat pulse flow measurement in action, and I just love this because it works with anything that works with Mother Nature. I really adore. So this is really just looking at using the difference between fractures with low head and fractures with high head to run water through the meter. And if you want to know anything additional about any of these tools, the USGS website is awesome. I mean, they have great explanations, even for chemists to understand. So we thought we would look at the water chemistry and see, does that support the geophysical data? Now, every water that is in the ground, if anyone's traveled, you know how it tastes different. And that's because there's small amounts of dissolved minerals that as the water passes through soil and rock, it picks up natural minerals from the water. So just, these are just small amounts of things like calcium, magnesium, and small amounts of chloride and the carbonates. And what you're looking at right here is called a Piper plot. And each one of those points on the plot represents the natural water chemistry of a particular sample collected from a particular well. So each one of those are different wells, including the water supply wells that I showed you the icons for. And in the triangles, the one on the left has got all of the positively charged minerals, and the one on the right has got all the negatively charged minerals. And what you do is you project them up to that diamond, and what we say is based on lots and lots of data and lots of experience at many, many sites, when you divide that diamond into quadrants, if the water's plot in a separate quadrant, it's highly unlikely that they're from the same source. So, the water's all plotting in that one quadrant here, which is in the circle. These were all waters from above 100 feet, bedrock and overburden, and the water supply wells, which were above 100 feet. Those are all not necessarily connected. That's not what these data are telling us, but they came from a similar water source. So that's really what that says. And whereas the two samples we had from the deeper bedrock wells plotted in a different quadrant, highly unlikely that those waters actually came from the same source as all of the waters above 100 feet. And this agreed with all of the geophysical data, told us that there really was very limited connectivity once you got below 100 feet. So it was nice to have this extra line of evidence. We also looked at the microbial data at the site. Many of you know that reductive dechlorination is the main natural attenuation remedy for chlorinated ethenes in the environment. And naturally, we found that to be not particularly active in the source area wells because you're pumping, you've got a lot of oxygen, you've got a high redox potential, not conditions conducive for the bacteria that do the dechlorinating to grow. So we looked at microbial populations in the source area, very low. I think they were even non-detect. We looked at them in the downgrading area, very low, not quite non-detect, but pretty low, looking at just the dechlorinating bacteria. But however, we have evidence that reductive dechlorination is going on. I mean, there's DC dichloroethylene and vinyl chloride and also ethene. So, where did those come from? Obviously, they came from reductive dechlorination of TCE. The total organic carbon, TOC, is fairly low, but my experience is in fractured rock that can be really low and you can still have reductive dechlorination. And I have not at all of the sites that I've done microbial work on the groundwater and fractured rock, I have not seen high populations of dechlorinators, even when there were tons of evidence that they were doing their work. It's just that they're not growing fast enough. Plus, the TC concentrations are fairly low, not really high that they would support robust bacterial growth. So just to summarize, the chemical data and physical data agreed with itself. And, we did have ERD, well, just reductive dechlorination. It's not enhanced at this point. We'll change that acronym, eh? So used to just saying the acronym, not thinking about what it means. So it's just RD, not ERD. The current remedy is working. It's effective for containment, but it's not really treating, it's not getting rid of, it's treating the mass, but it's not getting, treating it very fast. And we don't need to do anything. I mean, we're under remedy operation status. There's, everything is protected. There's no issues. But, is there maybe something we could do? Yes, maybe there is. So right now we're in the process of investigating what those somethings might be, or what that something might be. And, there's any in situ remedy is limited to contact. You got to have contact. Very difficult to achieve contact in fractured rock. The other thing is, the containment system is probably going to have to be a part of any remedy. You can't just shut it off and let the water supply get contaminated while you're worrying about getting rid of the DNAPL and probably maybe increasing TCE concentrations by what you're doing. And also, if you've got it, you gotta have to keep the pump and treat system operating. We have a lot of iron in our rock, so you get iron in reducing conditions, low redox conditions. The iron becomes water soluble. You bring it up to the surface into your pump and treat system. Add some oxygen. It becomes nice red slimy mess, and that's not going to help your treatment system. You're going to have to be doing a lot of maintenance. So, like I said, I mean, this is just we're just in the early stages of this, but just to take a kind of look at the table of some of the things that we're looking at, we're definitely looking at combined remedies, because any of these things would have to go with the pump and treat system as well. I mean, it might be times where we're looking at maybe shutting off a particular extraction well for a limited period of time, that might be okay. There's obviously, and I didn't mention modeling. There's been lots of hydro modeling, lots of the geochemical data were modeled as well. But okay, here's just the things main things you have to consider. Is it effective? Is it how is it? Can you implement it at fractured rock? And what are the relative costs? So here's just two possibilities. Like I said, I mean, we're totally in the initial stages of this, just even thinking about this. But we might do something like chemical oxidation if we could, maybe move peroxide around the pump and treat system. Could we possibly get the concentrations high enough? It is very short-lived. Or could we, put it in, shut the treatment system off for a little bit of time? I mean, it's not that, it's a great oxidant if you can get it in a high enough concentration, but maybe not. And then the follow-up being, could be enhancing reductive glucuronation. And when I say an injectable permeable reactive barrier, we have used the plume stop colloidal activated carbon in fractured rock pretty successfully in the past. So that may also be an option here. Right now, the source area concentrations are too high for that to even be considered. However, this might be a really good option for downgrading it, where maybe we could shut off one or two of the extraction wells, do this treatment downgrading it, still be protective. So thermal is also not the thermal like what Marianne talked about, where we're actually treating, but just to heat up the water a little bit. Heat it up, heat up the TCE. By heating up the water, get more of it out with the pump and treat system. And we could follow that up with enhancing reductive glucuronation. I mean, if you have just water that's 10 degrees C warmer, then the dechlorinated bacteria will double their rate of growth. So that can be a really powerful tool there. So this is totally in progress. Just I'm not even sure that these are the right combinations, but we do know that whatever we do, it has to also involve the pump and treat system. So, there's the big challenge. And, there's a summary of our slides, case studies, and where they overlap. And if you have any questions for Marianne and I, those are our email addresses. Feel free to email us.
Great. Well, thank you so much. Are there any questions about any of the case studies? I have one actually about the California case study, because there still does seem to be residual. So is there like a next step, or is that just finished?
Groundwater monitoring, sorry. So groundwater monitoring is part of the remedy. This comes down to the consent decree and, you know, previous owner, current owner, all that nonsense. But in general, I'm going to say no. Just let it go. No one's drinking it. No one's breathing it. All of the SSDSs have actually been decommissioned because water's down 20 feet below really tight soils. So there's no vapor intrusion issues to speak of. So just going to let it ride.
Okay, anything else? All right, well, I think we're scheduled for a break. So thank you again. Whoop.